For now.
Is it recording now? Yes, so everything you say, it will be recorded forever for future generations. Okay. Yep, so let's start. I have changed the settings, and now it's in Fahrenheit and imperial units. And you know that there are different tabs here. We have the basic. So in the basic, we just can calculate the old conditions of 1 point. Okay, so if I type here the dry bulb temperature, the relative humidity, we have the rest of parameters, the dew point, the enthalpy, the specific heat, everything, okay? Last Tuesday, sorry, we started using this process, okay? So we moved to this tab, and here we can see what happens between 2 points. And this is what we are doing now, because we have the air handling unit. We are heating up in winter. We are working winter now. So we are heating up the outdoor air until the indoor conditions. And it takes energy, okay? So by doing this, here we have the heating load or the cooling load if we are working in winter. Okay, so we don't have to calculate. We only have to type the right outdoor and indoor conditions here. So by default, there are 10. I don't know if you have the same, but in my computer, there are always 10 conditions by default. So let's get rid of all of them. Okay, so here we do not have anything. And now we can click here, this plus sign, and this is the first condition. So the first condition, let's say that this is outdoors. Usually the first condition, it's always outdoors. And we have to go from outdoors to indoors. And this is the heating or cooling load that we need. Okay, so outdoors in winter, it was 30 Fahrenheit, and relative humidity, 80, yes, 80. The second point, this is indoor conditions. So the indoor conditions, it's 70 Fahrenheit. I'm just copying data from the assignment, okay? And this is 40. Okay, remember that indoor conditions, it's something between 68 and 74 Fahrenheit, something between 35 and 55% of relative humidity. So those are comfort conditions. And now we are going from point A, which is number 1, to point B, which is number 2. Okay, so number 1 is outdoors, number 2 it's indoors. And now we have to calculate the dry airflow in pounds per hour. Okay, so I open this, and the ventilation airflow, when we have 500 people, so the ventilation airflow would be 500 times 20 CFM. Well, I'm not using, well, I'm going to use CFM. And that equals a lot. It's 10,000. And CFM, it's cubic feet per minute. Okay, this is the ventilation airflow. Now, if we go to the chart, we need the ventilation airflow in pounds per hour. Okay, so we have to transform a cubic feet per minute in pounds per hour. So let's do it. And how can we do that? It's 10,000. 10,000. So I'm going to do this because I think it's clear. This is cubic feet per minute. Okay, so now I have to multiply this times how many minutes do we have in an hour? It's 60 minutes. per okay. So that equals 600, yeah, 600,000 units cubic feet, because now we cancel minutes. And minutes. Okay, and now the units are cubic feet per hour. Hour. Okay, but we need pounds per hour. Okay, so we have to multiply this times. Well, we have to divide this by the specific volume. So the specific volume is 13 or something close to 13, and this is cubic feet per pound. Okay, so now cubic feet is cancelled with this cubic feet. This pound is moved up, and now this is 46,154 units pounds per hour. Okay, so be careful with units because we are talking about ventilation airflow can either be volume divided by time, or it can be mass divided by time. And we have this specific volume that relates volume and mass. Okay, it's the inverse of density. We can either use specific volume or density, but we have something to relate mass and volume, and this is it. Okay, but this is the airflow that we have with the right units, pounds per hour. So now it's 46,154. So we open the file again, and here on this dry airflow, we have to type 46,154. And that's it. We have written outdoor and indoor conditions. We go from point A to point B. The dry airflow is this one. And we only have to compute and draw the line. We submit. There you go. Okay, so this is outdoors. This is indoors. So we have to go from this point to that point. We have to increase the temperature. The temperature was 30. Now it has to be 70. And the relative humidity goes down. Okay, but and now we have to either calculate the difference of enthalpies. Okay, so if we go this, if we can do this with the basic option, and then we first have to type these conditions, then we have to write down this enthalpy, and we have to type these conditions, they have to write down this enthalpy, and then we just calculate the heating load. With this option, I have this point, I have this point, so the heating load is here. It's 10,353. Okay, so what is the heating power? Well, that's it's 10,355 BTU per minute. So be careful. Okay, this is the heating load. And we have BTU per minute. Why do we have BTU per minute? Well, because these are the units that we have here. We are used to BTU per hours. So we have to turn this into BTU per hours. So I can, okay, so let's do this BTU. That would be like this, and that would be minute. Okay, now we have to multiply times 60 minutes per hour. Okay, and and now let me do this 10,355 times 60. It's 621,300 BTU per hour. Okay, and this is power. It's not energy. There are, okay, with these units, the magnitude is power. So this is the final answer. Unfortunately, I don't know why, but this psychrometric chart is working in BTU per minute, and well, we need to give an answer in BTU per hours. Then, in this case, the air handling unit is working 24 hours in winter and 24 hours in summer. So if we want to calculate the energy, we have to multiply this times 24. So this is the power. If we want to calculate the energy, and if it's working 24 hours, we have to multiply this times 24, and whatever, it will be a few millions of BTUs, and then you have to divide by 100,000, and then you have therms. Okay, but BTUs is enough. I don't need the therm units. If you can calculate the therm, that's fine. But BTUs, it's good enough. But we need to understand the difference between BTU hours, the power magnitude, and the BTUs, the energy magnitude. Okay, so this is the first option. This is the first option, and you have 4 options. So we have already done this one, the winter condition with 500 people. Now you have to do the summer condition with 500 people and summer and winter conditions with 10 people. So at the end, you will submit 4 calculations like that. I don't know if you want to use these kind of things. Have you ever used the formulas in PowerPoint or in Word? This is a question.
No.
You have never used equations or formulas?
No, I don't think so.
Okay.
Yes, we have. At least, I mean, like the way that you're canceling them out like last year. Not, yeah,
Yeah, but
I had a math class that did that, and like, you know.
But have you used this menu insert equation here, or you haven't used that?
No.
Not in PowerPoint.
Yeah, I haven't used that before.
Okay, let me show you how it works because it looks more professional. I think this is clear enough because especially if we want to cancel minutes and minutes and minutes here and we end up having BTU hours, I think this is good. But the professional way, if we want to work on that seriously, I mean, if someone hires Keene State college students to work in a good company, well, I think it's good if you can use this. So here, I will stop. You have to insert first, and here you have equation and symbols. Okay, so let's work with equations. And here you have different samples. Okay, so we have all these math symbols. I don't think we need this, but if we have a division, we can use something like that. Okay, so we have to select something that it's similar to what we are using, and here we have the equation. And now it's easy because here we only have to change things. Okay, if we can type here 1000, and if we want to insert, for example, cubic feet per minute, we can always insert a fraction here, this one, and this can be cubic feet per minute. But this is not cubic. So what can we do? We can, before doing this, we can insert an exponential function here, like this. Okay, so here there will be cubic feet per minute. So it looks better. Don't you think so? I don't mind if you want to get used to using this kind of equations. It would be great because this is something professional. This is not professional. You cannot submit this in a professional report. It's good for a lesson or it's good for an assignment. But if you want to look something, yeah, if you want to prepare a professional report, you will have to use professional equations here. It's not difficult. It's you need to think what you have to do beforehand, and before doing anything else, what do I want to do? I want an exponential function here. Okay, so I can insert, or we can click on equation tools, and I want to insert or a radical, okay, or square root. Okay, so this is the square root of 56. And that's it. So if you, before doing anything, you think what you want, you only have to click here on equation tools, and what kind of, if you want a differential, okay, and here in this, no, in this integral, whatever, I can type whatever, x. Okay. So by using these equation tools, we can do whatever we feel like, and it will always look professional. And then you can always copy this equation to somewhere else, okay? And you can edit that equation. So once you are done with the first one, then you can copy, and then you can use this for different. I mean, this building science. Well, this is science, and when we are talking about science, we need to use professional equations with the right symbols. And I think this is the right way to do it. And you can use the same, if you insert in PowerPoint, you always have this. If you are opening Word, for example, here, insert, we have equation symbols, okay? So you can type the equation, and you can write here 43 divided to the 4th power. Okay, and then we have symbols. We have the Greek symbols here, so we can type all these symbols that we are using in math. It's a very useful tool. I'm not asking you to use it, and I'm not forcing you to use it, but if it's not for this course, if you get used to working with this kind of equations, I think, again, so little by little, we are building up our personality, and that's a way to express ourselves. So the more skills we have, the more things we can do. Okay, so using these kind of equations, try, and if you spend like 5 minutes doing this, it's very easy. So the only thing is that you need to use these equation tools, and that's it. Anyway, for me, the important thing is the final result and units. So if you have a nice equation, okay, that's better. I'll be happy looking at it. But the most important thing is that the result is the right one, and especially units are correct. Okay, so this is what we have done. Now the next. Now I want to prepare schematics of this. Okay, so I'm going to enlarge to make it bigger. And now the heating coil and the cooling coil. There you go. Okay, so we need something to heat up water, because a coil, it's something that, well, water runs through this coil, and then the air goes through the coil, and the air heats up, and the water cools down. But we need something to heat up this this coil, or the water going through that coil. And what can it be? It can be a gas boiler, it can be an oil boiler, a pellets boiler, whatever, but we need a boiler here. So if you open one of the nope, this one. Okay, there you go. If you open this chart with all the things that we are going to use, we can use a boiler here. Okay, so we can open this PowerPoint. This is for heating, so this is the boiler. And we can copy this here. So there will be a boiler. And what else do we need? Well, we need different things. So first, we can okay, we need a water pipe from the heating coil to the no, from the boiler to the heating coil. We need okay, I have here different examples. So we're going to need expansion tanks, and we're going to need water pumps. So I can copy those things. Okay, so there will be a water pump here, pumping the water from the boiler to this, and there will be an expansion tank here at the beginning of the circuit. Okay, so there will be an expansion tank here. And then we have to connect this here. Okay, so this is the from the boiler. It can be gas, oil, whatever. We're not talking about this kind of boiler yet. So we need a water pipe to the heating coil. And then from the heating coil, we would need a return. So that would be red. It can be thicker. And I told you that when we are using this return, we can work with this dashed line. Yeah, I think that looks better. There you go. Okay, so we are moving water in this direction. We have the heating coil, and then the air heats up, the water cools down, and we go in this direction. We go back to the boiler, and then we heat up the water again, and we have a closed loop here doing this. Okay, so do we have everything we need here? No, we need something else, because we have to get rid of the okay, so we have all these gases, and we have to get rid of it. So from the boiler, we need a chimney to get rid of the gases. And then we have the air handling unit. We have the boiler with the water pump, the expansion tank, heating coil, and we need something similar with the cooling coil. What can we use to cool down water? Okay, so here we have a chiller. This is a chiller. We should open this catalog. Yeah, so that would be better. And this is the chiller. Okay, here. So we copy this one. We can place the chiller somewhere here. And then we need the same, we need the same elements in a different direction. And with a different color, because this is cold water. So we have to change the color of this thing. I'm going to change it. There you go. That's better. And now we need another dashed line, a blue one. Okay. So this is it. We have everything we need here. We have water pumps and expansion tanks. Every time we have a closed loop, we should have this. Someone might say that in the cooling circuit, we don't need an expansion tank. Maybe they're right. Anyway, you can talk to the mechanical engineer, and he doesn't think that you should use an expansion tank. We can always remove it, okay? But I would place the expansion tank here. But in cooling circuits, yeah, in heating circuits, closed loop circuits, for sure we would need an expansion tank. Here, maybe it's not necessary, but anyway, it's there. And then we have this and that. So this is the schematics, and now we can, what do we need? So we need numbers here. And what are the numbers? We know the heating load, and this power here is the power of the boiler. Okay, so if we place here the power of this boiler, and then you will calculate the cooling loads, and this is the power that you need for that chiller. Okay, so this is something meaningful. It's not just a nice drawing with colors and arrows and whatever. No, we are connecting things, and we are connecting the heating coil to the boiler, the cooling coil to the chiller, and we're providing useful information about the equipment, okay? So this is the boiler, and this is the power that we need. So if we go to a catalog, we need to find a boiler whose power is larger than this one, okay? So it has to, we have to be above the calculated power. This should be the minimum. So if we won't find in a commercial boiler 621,000 and 300 BTU hours. Maybe we would find 700,000 or 800,000 or 650. Okay, but we need we need to know that the boiler that we are going to use has to be above this number. So this is what the schematics is. So here we have everything we need in our system. We have ventilation, because now we are introducing fresh air here. We have the air handling unit. We have the device that heats up water, and we have the device that cools down water. And if we want to make it more, if we want to give more data, we can always copy and paste the indoor conditions, and we can copy and paste the outdoor conditions. Okay, so we have a lot of information here. We have the outdoor air at 30 Fahrenheit and 80% relative humidity. We go through the heating coil. The boiler is running, is working. This is the power that we need for that boiler, and this is the final condition of the air. Okay, so this is looking like something professional, because something professional, we have to commit to writing accurate data. So we have data here. So we have the indoor and outdoor conditions, and we have the power of the devices that we have. The more things we know, we can specify the power of this circulating pump. We can specify the volume of the expansion tank. We can specify the diameter of this chimney. We can specify the thickness or the width of those ducts. Well, there's something else we can write, which is the airflow. So we know that the airflow, we have calculated it, and it's 10,000 CFM. Okay, so now there's a lot of information. So if we print out these schematics and we email these schematics to the company, the provider of the heating and cooling systems, they know what to do. Okay, I have this airflow. I have this power for this. I have the air handling unit with a cooling coil and a heating coil. Okay, I know what to do. So we don't need anything else. And now a company, a provider of mechanical systems, can supply this to that place, and they can install it in our building. And it's not a building. We haven't designed any buildings yet. So where is this? Well, I don't know. We have to place the air handling unit. Usually it's on the roof. Where are the chillers and the boilers? Well, usually they are on the basement. Okay. So we have to work more, and that's why we're using Revit now. So in Revit, the first exercise, we need a building, and then we need to place the air handling unit, we need to place the boiler, and we need to place the chiller, and then we have to connect all these to the heating and cooling coils. We need water pipes here, and we need air ducts there. Okay, but first, everything is connected. So I want you to understand that our calculations are connected to these schematics, and these schematics is connected to the final Revit model that we are working with. Okay, so it's not that, okay, there would be something, no, I only use Revit. I don't want to make any calculations. Why not? No, or this is those kind of drawings. Yeah, this is for engineers. Architects don't do that. Why not? But what we do, so if you don't want to use Revit, you don't want to calculate anything, you don't want to draw or to work with these schematics, and you don't want to use Revit, then you are not an architect. I mean, you are something different. Okay? But eventually, we will, if we know how to work in different aspects of the same problem, so we are good architects, that we are able to do a lot of things. Anyway, So we go step by step. This is the problem. So in the problem, we need data, outdoor temperatures, number of people, indoor temperatures, what kind of systems we want. Then we have calculations. Calculations are important because the power, the size of the heating system, the size of the boiler depends on the power. The more power, the bigger the boiler, usually, okay? So we need this because it will affect at least the size of the equipment, and it will affect the size of the mechanical room. And then we need to connect things. We need to know that there are different things, and we need to know what to connect. We have to connect the boiler to the heating coil, the chiller to the cooling coil, okay? And finally, we have to place things on the building. So this is this can be on the basement. We can design a mechanical room on the basement. And this, usually those air handling units are on the roof of the building. Okay. But this tool, we can make the most of this tool, and we can, I think we can do something else. How? I'm going to open again because it's wonderful, it's for free, but it's not it's unstable, this tool. So sometimes you have to close it and open it again. Because if you want to solve different exercises without closing and opening again, sometimes it doesn't work. Okay, so remember that we have to adjust the settings, reset inputs, submit, Fahrenheit. So now we are not working with the process, we are working with cycle 1. Okay, so in cycle 1, we are doing something different. So in this cycle 1, if we want to state the problem, okay, what are we doing here? Well, probably we need something else. So our air handling unit should be bigger. We need to add another module. Okay, and that module would be the heat recovery. A heat recovery, it's like a square like this. Yeah, kind of. And that will be the heat recovery. Right. Okay, so now we have a cooling coil, we have a heating coil, and we have a heat recovery. I'm going to place this here. Okay, and how does it work? We have to recirculate the air. So we have the air supply here, and then we will have the air return. So we can copy this, and now we have to move this air up. There you go. Okay, perfect. So we need to recirculate the air. So we have the air supply, the air return, and if we include arrows, I think it will be even better. There you go. Okay, we supply, then we return the air, instead of getting rid of the air, we just recirculate the air to the air handling unit again. Okay, and here we have the heat recovery. So in this heat recovery, we are mixing up this air at these outdoor conditions. So we're mixing air at 30 Fahrenheit, 80% of relative humidity, and this air is at these indoor conditions. So after going through this heat recovery, we need that indoor conditions here. So the air at the supply is at these indoor conditions. But before, let's remove the cooling coil. Before the heating coil, we might have changed these conditions. And maybe this is not 70 Fahrenheit. But it must be, let's say, 50. Okay, so by mixing this air at 70 Fahrenheit with this air at 30 Fahrenheit, it would be something in the middle. It depends on this flow, it depends on the efficiency of the heat recovery, but the idea is that we recirculate this air because we have a lot of energy on that air. So it's a shame getting rid of that energy without making the most of it. So that's why we have the heat recovery. So this is our, this is what we are going to do now. Okay, so this is the basic thing. We need to, probably we would need another. Okay, so now we supply the air, and with the air gets, yeah, we can release moisture, particles, viruses, whatever, and then we have to get rid of it. Okay, so just get rid of it. But if we recirculate this, we will improve the efficiency of the system with that heat recovery. So this is what we're going to calculate now with this. Okay, so look at this. So we have the fresh air, but we return this and we mix. So this would be the heat recovery here. Okay, so if you see this small picture here, we can understand what we are doing. We are supplying air here, and then we are getting rid of this air, but part of this air is mixed with the fresh air here. So we can extract some of the energy that this return air has. Okay, so this is what we are doing with this cycle 1. We have a cycle 2, but it's more complicated, so we are going to use cycle 1. And what are the inputs here? We need the indoor and the outdoor conditions. So the indoor conditions, again, it's 70. Relative humidity, 40. The outdoor conditions, this is 30 Fahrenheit. And relative humidity, 80. Okay. And here, this is the fresh air ratio. If it's 50%, that means that the efficiency of this heat recovery is 50%. Okay, so we are extracting 50% of the energy that we, that we have in this return air. That depends on the efficiency and it depends on other things, okay? But it's a question of the efficiency of the heat recovery. If it's 50, it's fine. If it's 60, it's better. And if it's less than 40, I think it's not worth having a heat recovery. Okay, so those efficiencies goes from 40% to 60%. It's our responsibility to select the best heat recovery, but it's not easy because it depends on the heat, on the airflow. It depends on the outdoor and indoor conditions. So we need to rely on mechanical engineers to select this kind of heat recoveries. But at least we can deal with them. Okay, what's the efficiency of the heat recovery? It's 55. 55, quite good. Because if the efficiency is below 40, it's not good enough. If it's above 50, it's a good one, okay? But at least we can deal with them and we can talk to them. Here we have a heat load. This is an extra heat load that we can apply here. So we are just mixing these two airs or airflows. So here we type 0 in this heat load, okay? So remember the fresh air ratio is 50. This heat load, let's type 0. And what else? Do we have to decide something else? Well, here we have to select winter. So you see weather, summer, winter. So we select winter. And we have the ventilation flow. So the ventilation flow in pounds per hour, we calculated that before. I have it here. Yeah, it was 46,154. This number comes from here. Okay, you remember that figure? That was the ventilation flow in pounds per hour. And this is what we have to include there. Where are we here? Okay, so indoor conditions, Fahrenheit, temperature, relative humidity. Outdoor conditions, temperature, relative humidity. Fresh air ratio, this is the efficiency of this device, the heat recovery, let's say 50. Heat load, we are going to say 0, because we can apply some heat load here, and we are going to analyze the heat load of this heating coil here. The ventilation flow, the same ventilation flow that we calculated in the other exercise. Type winter, because those are winter conditions. And now compute and submit. See what happens. Okay. Well, as you can see here, we have something more complicated. When we select process, we go from point 1 to point 2. Here, we go from point 1 to point 2, but by mixing up airs, by heating. Okay, when we move horizontally towards the right, or rightwards, that means that we are heating up the air. Okay, so you see that we are moving horizontally here, and we're moving horizontally here. And when we have two different air flows, and we mix them, we have a point here which is in the middle. If we have selected 50, okay, so that point should be in the middle between the outdoor conditions and the indoor conditions. So it's just in the middle. And then this is an enthalpy, and then we have another heating load here. Okay, so we have saved energy. We have saved energy because at the beginning we have to go from this point to this point, and we just have the heating coil. Now we are mixing these two airflows with the heat recovery, and this is different. How can we check that? Because you have a heating load now, which is 5,176 BTU per minute. Okay, remember that figure is 5,176. So in this case, we can write that the heating load equals 5,176 units. BTU per minute. And now we have to multiply this times 60 minutes. per hour. Okay, so my heating load is 5176 times 60, 310,560 BTU hour. Okay, so by using this heat recovery, my heating load is 310,000. What was the other one? There you go. The original one was 621,000, and this is 310,000. So what's the moral to the story? We have saved energy. We have saved around 50% of the energy. Isn't it amazing? Yes, it is. You might think that energy, blue, hot, blue. Okay, but it's a lot. Okay, just by doing this, we have complicated our lives because now we have to, what do we do with this duct here? In this case, we didn't need that duct. So now, from the architectural point of view, this is more complicated because we have a terrible duct here that we have to hide, and it's more difficult for us. So for us, it's easier. Okay, I have a device here, and I have a grill here, another grill there, and that's it. There are no ducts. With this option, yeah, what do I do with this? It cannot go. I have drawn the duct here on the roof. Usually they are not on the roof. We have to. Yeah, so this is inside the building. Those ducts going from the air handling unit to the room, and from the room to the air handling unit, there should be inside the building. Okay, so this is a nightmare. So it's okay. What do I do with this? But in terms of energy, there is no question because I'm saving half the energy, and this is a lot. And I'm saving half the money. It's not, if you don't want to think about energy, think about money. And for sure, our client would be extremely happy if he's paying half of the electricity bill that, or the energy bill that he should pay. So is it clear what we have done? We're calculating, or we are solving the problem, but in different aspects. We have to understand the problem, and understanding the problem is the winter, summer, outdoor conditions, indoor conditions, number of people, CFM. We need the air handling unit, we need heating, cooling, and ventilation, so we can do everything with the air handling unit. Okay, so let's do it. Let's calculate everything. We calculate things. Then, okay, let's connect things. So we have the schematics, and I have this, I have the air handling unit, boiler, chiller. I have to connect all these things. I have to get rid of that gas. I need the air inlet, the air outlet. Okay, so I have solved the problem. Now I can save energy. Okay, if I want to save energy, I'm not doing anything different. I'm just, by the way, I did this with 500 people. Okay, so I'm not changing the design of the building. I'm changing the ductwork. Yeah, so it's complicated, and I have to think, oh, now I need to hide this duct. How can I do it? Okay, it's more work on architects, but it's worth it because we are saving half the energy or half the money for my clients, and I'm saving the planet, and I'm all that stuff. Okay, but first I save money. This is what our clients will understand. Then we have to be happy with our work, and we have done the best, or we have worked to the best of our knowledge. Okay, if we know that there's a better solution, but we are lazy and we say, now let's, yeah, I'm going to charge the same if I use this solution or if I use that one, so I don't mind. No, we have to be committed to a good quality, and then we have to save the energy. Are we done with this? No, we're not, because now we have to do the same thing, but using Revit. And well, this is what we are going to do now. But I think so far this has been the most important lesson that I have given in this course. Okay, because if you look at the psychrometric chart, what is this? It's to where do I have a psychrometric chart in a room, in a real building? We don't have psychrometric charts there. But we have to understand that by using psychrometric charts, I can end up calculating energy savings, and it comes at a price. And the price is that I have to deal with this. So I have a building and I have this monster somewhere, usually on the roof, and I have those monsters, the ducts. Okay, so now we have to hide the monster. But we know that it's worth it because I have saved a lot of energy. Okay. So let's open Revit, and what can we do? I don't know. I'm going to give the first introduction to a Revit lesson. If you have never used Revit, do not panic because we are going to use the mechanical template. So even people that have taken CAD 2, they don't know anything about mechanical templates. I guess maybe you are experts. If you are, let me know, and I will give you more advanced lessons. But if you don't have any idea about using mechanical templates, we will start from scratch. So first, we have to open a new. And here you see that we have different templates. We have the construction, the architectural, the structural, and the mechanical template. Let's use a mechanical template. Okay, so apparently nothing has changed. It's the same Revit issue. And sometimes here on this properties window here, we have discipline. And in disciplines, we have architectural, if you click here, structural, mechanical, electrical, plumbing. Okay, so let's work with a mechanical discipline. Okay, so we have to open a mechanical template, and we have to open this discipline. We have to change this discipline to mechanical. Why? Because something might not work correctly if we are not working with this mechanical discipline. Okay, and then I think with this mechanical template in here, you can work with walls like this, okay? But usually we don't do that. So we are, and as you can see, when I'm working with these walls, I cannot edit them, you see? This is because I'm working with a mechanical template. So we are not working with an architectural, or we cannot select the walls and we can't modify these. So working with a mechanical template, we can't design architecture. So usually we work with a Revit design, with the architectural or construction template, and then we insert or we import the architectural model to the mechanical template. So this is what we're going to do now. So here we have architecture, structure, steel, systems. So we have to insert. So we can insert from file. Okay, so we can insert this Revit file here, or this Revit link. Okay, so I have already modeled an architectural template. So I'm going to insert this. Okay, you see, it's a masterpiece. Okay, but I have already done this in using the architectural template of Revit, and now I have inserted this into the into another discipline. Okay, so now we are going to start using systems. So here we have architecture, structure, steel. In structure, you have structural things. In steel, you have steel connections and welds and bolts and whatever. But now we are going to use systems. So far, we are going to use only 2 tabs. We have a lot of tabs here. We are going to use air terminals, and we are going to use mechanical equipment. By default, I don't think you have mechanical equipment by default in Revit. So we have to type here, and we usually have this message: no mechanical equipment family is loaded in this project. We have to load mechanical families. So this is my terrible Spanish Revit. I don't know why this happened. Anyway, you have to go to a library. So you will have, this is the most important thing. You have, when you are talking about mechanical, so you have to open this folder, mechanical, and then you have the architecture, and then you have the MEP. When we are working with a mechanical template, we have to use this MEP, because the architecture, you have the model, the 3D model, but you cannot edit, you cannot insert ducts and pipes. So we have to use always this MEP folder. Okay, so we open that folder, and we have a lot of things. So these are ventilation things, and here we have air control units. So you have to type air control units, and here we have a lot of things. So I recommend you click one of them, and then you can go over, and here you can see what kind of things we are. There are a lot of things. This is too advanced. So I recommend you use this one, because this is an air handling unit. Here we have different modules of different air handling units. So you can manufacture your own air handling unit, but this is too advanced. So you will find this exterior air handling unit, horizontal. Okay, so if you open this element, so here we have the exterior air handling unit, horizontal, and place it somewhere. There you go. And you see that, I will make it wireframe. You see that when we select this, there are a lot of points, and those points are connections. Okay, so as of those points, I can draw air ducts, water pipes, whatever. So usually when we have something like this is water, this is out, this is in. Okay, so that would be the heating coil or the cooling coil. We have an outlet for water and an inlet for water. And the biggest things here, we have an out, which is the air duct, and this is an intake, which is another air duct. And this is intake of fresh air. Okay, so look at this air handling unit. We have the return, well, we have the outlet, so we move the air from this point to the building. Then we return the air to this place, and then here we introduce the fresh air. So it's the same thing that we have seen. So it's this. Okay, so this is we are moving air from the air handling unit to the building. We are getting fresh air from outside, and we are recirculating the air here. So this is what we can find in Revit. But this is the actual, so air handling units are like this. They are boxes with all these things. And these are the coils. You see that here we have two things. So this is the water outlet, water inlet, outlet. So those are two coils. One would be the heating coil and the other one would be the cooling coil. And these are the air ducts. Okay, so first, where is this air handling unit? Okay, by default, if we have two levels, level 1 and level 2, by default, this is on level 1. So we have to select this, and then we have to click here, level 2, and we can move it up. Elevation offset, I think if we do this, 3. Okay, it doesn't change. What if I select this and then move it? Okay, that works. Okay, so it has to be, because it was on level 2, but it has to be above the slab. Usually this is not just on the slab because it makes, it vibrates, it makes a lot of noises. So we need to, yeah, we need some legs, and we need something, well, placing this because it's, it weighs tons. Okay, so we need a structural reinforcement. So knowing where these elements are, it's important even from the structural point of view. So we cannot have a building and say, okay, where do I place the air handling unit? There, boom, because the building will collapse. Okay, so we need to know beforehand where to place all these stuff. Okay, so this is my air handling unit. Beautiful. Now, what else? I told you that we are going to use only two elements now, the air handling unit, and on systems, we have the air terminals. So the air terminal, again, no air terminal is loaded. So we have to select air terminals. And now there are plenty of things. And instead of, because I don't know the name, but I know what I'm looking for. Okay, I'm looking for this. You see, this is a supply air terminal or a supply diffuser. But we are looking for this one. We open, and let's place one here, 1, 2, and 3. Okay, so we have the air handling unit and 3 air terminals. Now we have to connect things. Well, first, I think we should see the east elevation. Okay, you see, those air terminals are on the floor. This is not acceptable. They are on level 1, but we need an elevation from that level, let's say 10 feet. Okay. Okay, so now it can be here. So those are the air terminals, and this is the air handling unit. If we look at the 3D now, so the easiest way to work with this, we can select. Be careful that you don't select the building itself. You have to select only the terminal units, the air terminal units, and the air handling units. And then you can click on duct. This is supply. We can design the return, but this is only the supply. We can click OK. And now we generate layout. Okay, so here, you type here, generate layout. And we have this terrible layout, but you can change. Okay, so there are different layouts here. I don't know which is worse. Let's say this. And now we click OK. And we have this terrible thing. Why is it terrible? Here we have this kind of ducts, but at least we have connected the air handling unit to the air terminals. This is not good at all. Okay, so I'm not happy at all. But at least we have a connection, we have a system, and then we can start editing the system. But as you can see, we have something similar to the problem here. Okay, those are the terminal units. Imagine that instead of a terminal unit, we have 3. One, 2, and 3. And here we have 3 arrows. Like this. And well, this is important because the total airflow, it was 10,000. Okay, so the total airflow is 10,000. If I have 3 different diffusers, now the airflow through each diffuser would be 10,000 divided by 3, which is okay. Vale. Okay, so each diffuser, let's move it here. There you go. Okay, so we have 10,000 here. Through this diffuser, we have 3,333. Through this one, we have 3,333, and this one. Okay. Why do we do this? Because it's better. If we had only one diffuser here, it would be very difficult that all these people are feeling the same temperature, the same airflow, the same air speed. But if we distribute evenly the diffusers through the room, the comfort conditions would be better. So that's why we need to use different diffusers. It doesn't affect the heat power or the power or the heating loads, but it will affect other things. Okay, so we will end up calculating those ducts and we will select as many diffusers as we need. And then we need a return. We're not designing the return with Revit so far, okay? But this is what we have done. We have calculated this. We have calculated the power. Then we have these schematics with all the devices that we need. And now I'm starting placing devices in Revit. So in this Revit file, I have already placed the air handling unit. I have to work with the ducts, because this is not acceptable. So I have to make something nicer, but we have the whole semester to do something nice here with all these ducts. And finally, I need to place in mechanical equipment, there will be, or we can insert load families. And here in load families, I'm sure that there are in this MEP, well, we have heat pumps, we have boilers. We're not going to use this yet, but we have to place the boiler, the chiller, the heat pump, whatever, somewhere in our building. And then we have to connect with water pipes those elements to the air handling unit.